Now that we have a general formula for computing the surface area of solids of revolution, we want to look at an example of how to actually do this. One observation that I would like to make before we begin, though, is that here we had a function f of x, and when we're computing the surface area of the solid of revolution formed by revolving the curve y equals f of x about the x-axis, it's important here that x is the same variable as the axis of revolution. So in this case, the variable with which we're integrating with respect to, it has to be the same as the axis of revolution. So that variable of integration has to be the same as the axis of revolution in order for us to use this formula. So keep that in mind here as we do example 5, and we're going to look at example 6 in addition. So example number 5 says compute the surface area of the solid formed by revolving the graph of y equals root x on the interval 1, 7 about the x-axis. So here, if we draw our usual picture, we are interested in the interval from 1 to 7. The square root of x looks something like this on that interval. And if I revolve this about the x-axis, I get some surface that looks like this. Cool. All right, so we've got a surface here. And what we want to do in order to compute the surface area is we know we need to integrate the surface area of a given shell. A given shell, let's see, we're integrating from 1 to 7, which is the left end to the right end. A given shell is going to have radius 2 pi times square root of x, so 2 pi times the y value on the curve. And it's going to have length equal to the usual length differential, which is root 1 plus the derivative squared. So maybe we'll just write that as dy dx for the moment, squared dx. Great. So here's the thing that we need to integrate. We know in this case that since y equals the square root of x, we can write down dy dx as 1 over 2 root x. And then we have integral from 1 to 7 of 2 pi root x root 1 plus, let's see, dy dx in this case is 1 over 2 root x squared dx. Certainly doesn't look like an integral that's very easy to do, so we are left with kind of resorting to simplify the integrand, see if it looks a little bit nicer when we're done. So let's see, 1 to 7, we have 2 pi floating around still. Square root of x, we have the square root of 1 plus 1 over 4x, it appears. In order to continue simplifying the integrand, the observation that I want to make here is that if I were to distribute, or I can combine these square roots. That's the first observation that we want to make. Combine the square roots. So let's see. So I'll have x times 1 plus 1 over 4x. And if I now distribute the x, things look a little bit nicer for me because I've got 2 pi square root of x plus 1 over 4 dx. So this looks better because this is the square root of some linear function of x. And linear functions of x are pretty nice because that means we can do u substitution with them. So if, or a fairly straightforward u substitution, namely if u is x plus 1 over 4, then du isn't going to have anything associated with it other than maybe a constant times dx. In this case, it just is dx. So at kind of the moment, we've done a lot of practice with these u substitutions, so I'm going to start working on them without showing you all of the details of the u substitution. In this case, you can probably guess that the antiderivative here is x to the 1/4 to the 3/2 times 2/3. We want to evaluate from 1 to 7. So sort of how I knew to do this, I know this was x plus 1/4 to the 1/2 power, so I knew that I was going to raise the exponent by 1. If I were to take the derivative of this thing here on the right-hand side, the 3/2 would cancel out with the 2/3. I would decrease the exponent by 1, giving me the necessary 1/2 power. But I would need to multiply by the derivative of the inside function here. But fortunately, the derivative of x plus 1/4 is just 1. So there's no additional work that needs to be done in order to deal with kind of the derivative of this inside function here. So let's see. So now that we have our antiderivative, we want to actually evaluate. We have a 4 pi over 3 hanging out front. And we have, we're adding 1/4 to each of these and raising them to the 3/2 powers. So 7 plus 1/4 is going to give me 29 out of 4. We're raising that to the 3/2. Minus 1 plus 1/4 is going to give me 5/4. And we're also raising that to the 3/2. Great. So we have a surface area of our solid of revolution here. All right, not so bad once we did the setup. So let's take a look at another example. So example 6 is asking us to compute the surface area of the solid formed by revolving the graph of y equals x to the 1/3 on the interval from 1 to 8 about the y-axis. So here we want to again draw our picture. We have x to the 1/3 on the interval from 1 to 8. We know that we have a curve that looks something like this. This time, however, note that we're revolving about the y-axis. So I'm taking these pieces here and I'm revolving them about y. In order to think about now the surface area, what I want to do is I want to integrate with respect to y. In particular, because I'm revolving about the y-axis, and we made this observation earlier, that when we use this formula, the variable of integration has to be the same as the axis of revolution. We need to integrate this with respect to y because we're revolving about the y-axis. There's no real way around that. So let's think about what is going on with this integral then. So we need to integrate from the bottom point to the top point this time. So we need some y values here. So the y-coordinate on this left point here, if I take the cube root of 1, I get out 1. The y-coordinate for the top point is going to be the cube root of 8, which is 2. So we're ranging from 1 to 2 here. I want to take 2 pi times the x-coordinate of a point on this curve here. In particular, I want to take 2 pi times an x-coordinate because the x-coordinate is the radius of the shell that I get by revolving a small length segment about the y-axis here. So 2 pi times the x-coordinate, well, I don't quite have a formula for x-coordinates yet, but if I take my y equals x to the 1/3 equation here and I cube each side, I get y cubed equals x. So my x-coordinate is given by the formula y cubed. And then what I want to do is I want to take the square root of 1 plus, in this case I want dx dy, because that is my length differential, dy. All right, cool. Well, again, with our formula for x in terms of y, we can compute dx dy fairly easily. Dx dy is going to be 3y squared. And so moving on, we can integrate from 1 to 2 here. We have 2 pi, we have y cubed, square root of 1 plus, let's see, we have 3y squared, which is 9y to the 4th dy. And now with this, we can look at it, and now we say that we notice that we can do a proper u substitution here because I have a quartic inside, that means a 4th degree polynomial, and its derivative will be some multiple of y cubed, and so a good idea here would be setting u equal to 1 plus 9y to the 4th. So in this case, du is going to work out to be 36y cubed dy, which is to say that du over 36 equals y cubed dy. So I've got this dy, or y cubed dy in my integral there, and so I can replace things. A y value of 1 corresponds to a u value of 10. A y value of 2, well, 2 to the 4 is 16. 9 times 16, I believe, is 144, plus 1 is 145. And I still have 2 pi. That y cubed dy is going to become a du over 36. And I have a square root of 1 plus 9y to the 4 is u. Cool. So my integral simplifies into something that I know how to do here. I have 2 pi over 36, works out to be a pi over 18. And then I'm integrating the square root of u. Well, that's u to the 1/2, so the integral becomes u to the 3/2 times 2/3. And I'm evaluating from 10 to 145. So putting everything together here, the 2/3 and the 18 combine to give me a denominator of 27. I'm evaluating u to the 3/2 from 10 to 145, so I get something like 145 to the 3/2 minus 10 to the 3/2. Cool. So again, we have kind of an answer for a surface area. Now, the question that you might be asking right now, or maybe you don't want to be kind of railroaded into forcing the integral here to be an integral with respect to y. And in fact, we don't have to in order to do this problem. We totally can integrate with respect to x. We just have to think a little bit about how we might do that. So if we want to integrate with respect to x, we want to think about, again, sort of taking the integral from, well, the left endpoint to the right endpoint. So that's 1 to 8 here. Now what we want to think about is what exactly is the surface area of sort of one of these shells that we're creating here. So now since we're revolving about the y-axis, my shells look something, ooh, that's pretty bad. My shells look something like this. And so the surface area of one of these guys is still going to be the length of this kind of diagonal piece here times 2 pi times the radius of this sort of circle that we've drawn here. So the length of that purple bit is again going to be square root of dx squared plus dy squared. And the circumference of this circle now, well, since I'm revolving it about the x-axis, or the y-axis, excuse me, the radius of this circle is now going to be the x-coordinate of the point that I chose. So here what I'm integrating is 2 pi x times the square root of this thing. And I want to integrate, I'm thinking about using x as my variable here. So when I'm factoring out of this square root of dx squared plus dy squared, I want to factor out a dx squared to give me 1 to 8 of 2 pi x times the square root of 1 plus dy dx squared dx. So we can now integrate with respect to x. We know, for instance, we're using the formula here that y equals x to the 1/3, and so this tells me that dy by dx is equal to x to the minus 2/3 out of 3. So we can substitute into this integral here, integral from 1 to 8 of 2 pi x square root of 1 plus dy dx squared is x to the minus 2/3 out of 3 squared. And simplifying a little bit further gives me the integral 1 to 8 2 pi x square root of 1 plus, let's see, we're going to have an x to the minus 4/3 here over 3, oh, nope, over 9 dx. And if you sit down and you play with this for a little while, this is going to be a pretty difficult integral to do. But there is a trick to this one, and this trick is kind of clever. It's not one that maybe I would expect you to come up. It's certainly not one that I would expect you to come up with on a test. Maybe if this were like a challenging homework problem or something, perhaps. But what we want to do here is we want to split up this x into x to the 1/3 times x to the 2/3. Square root of 1 plus x to the minus 4/3 over 9 dx. And now what I want to do is I want to think about that x to the 2/3 as, let's see, so we still have this 2 pi x to the 1/3 here. The x to the 2/3, I want to think about it as the square root of x to the 4/3. Because what that's going to allow me to do is get rid of that x to the minus 4/3 power inside of the square root there. So I'll combine the radicals, integral from 1 to 8, 2 pi x to the 1/3. So let's see, so now I get the square root of x to the 4/3 times 1 plus x to the minus 4/3 over 9 dx. And distributing in that x to the 4/3 now gives me the integral from 1 to 8, 2 pi x to the 1/3 square root x to the 4/3 plus 1 over 9. Whew. All right, so after all that arithmetic, what exactly did that get us? Well, notice that the thing under the square root here, this x to the 4/3 plus 1/9, its derivative, which is something times x to the 1/3, is floating around outside of the square root. And so what we're going to do here is a u substitution involving with u being that x to the 4/3 plus 1/9. Great, so now that we have a little bit more room to work, let's do that. So let's work with the u substitution. U equals x to the 4/3 plus 1/9, so that du is 4/3 x to the 1/3 dx. We have the x to the 1/3 dx, so let's move over the 4/3 to become 3 du out of 4 equals x to the 1/3 dx. And we can actually do this integral now. So let's see. So we have the integral from, we should maybe think about changing my x values here. Actually, tell you what, we're going to maybe do that later. No, we'll do it now. X equals 1 corresponds to a u value of 1 plus 1/9, which is 10 out of 9. And an x value of 8, well, if I'm using x equals 8 in this equation here, I get 8 to the 1/3 is 2, to the 4th is 16, and 16 plus 1/9 is going to be 145 out of 9. So you can see that this is shaping up to give us some similar numbers to what we had before, where this 10 and this 145 are going to play a role. So let's see. So we still have 2 pi out front. X to the 1/3 dx becomes a 3 du out of 4. And now we have the square root of u, and we want to simplify this, or we want to actually integrate. So let's combine some of these terms. So 2 out of 4 is going to give me a 2 in the denominator, a 3 in the numerator. So we have a 3 pi out of 2. The integral of the square root of u is going to give me a u to the 3/2 times 2/3. And I'm evaluating from 10 over 9 to 145 out of 9. The 2/3 and the 3/2 constants cancel, so that's going to give me pi times, let's see, u to the 3/2 evaluated at these points is going to be 145 to the 3/2. 9 to the 3/2 is easy to compute because 9 to the square root of 9 is 3, and 3 cubed is 27. Minus, again, a similar argument here holds, 10 to the 3/2 out of 27. And I can factor out that denominator of 27 to give me pi out of 27 times 145 to the 3/2 minus 10 to the 3/2. And if you go back and you compare kind of these answers here, this pi out of 27 times 145 to the 3/2 minus 10 to the 3/2 has already shown up. We got that answer when we integrated with respect to y. So we can see that either of these approaches works just fine. Again, kind of one of them was a little bit more work, though maybe it's not obvious which one was going to be more work from the get-go. So again, you sort of have to do a bunch of these problems and maybe develop some intuition for which approach is going to be best. And sometimes you're just going to pick poorly, and you have to go back and try the other method, or you have to suffer through a little bit of arithmetic in order to actually do an integral here. But in any case, both of these methods give us the same answer, so whichever one you prefer is more or less functional, at least for this problem.